So welcome back, everyone. I hope the launch was great and you enjoyed, and I hope you will enjoy the session as well. So we have Maya Costantini here and Anderson Sasaki. They will be talking about bootstrapping and maintaining trust in the cloud with Keylime. I hope you enjoy it.
Thank you. So first of all, to introduce Keylime, let's try to see what problems does exactly Keylime solve. So we know that trusting remote machines that are not under direct physical control can sometimes be a significant challenge, and in particular in environments such as edge, IoT, or any cloud infrastructure that does often not belong to you directly. So our goal with Keylime is to protect sensitive workloads, even when they operate within less secure remote environments. So the question is, how can we be certain that devices in those environments run as intended? And how do we ensure a particular workload is not being executed on a compromised machine or virtual machine? So what is Keylime? So Keylime builds on existing hardware and Linux technologies that include TPM, TPM TSS, and IMA. It represents an evolution of integrity verification, and it enables remote monitoring of thousands of nodes. Keylime provides remote trust verification and covers measure boot and runtime integrity. So a bit of history about the project. It was started in 2016 with a research paper entitled Bootstrapping and Maintaining Trust in the Cloud that was published by the MIT Lincoln Labs along with a prototype. Then in 2018, a community was created around Keylime, which we can explore on GitHub under the Keylime organization. And by 2020, Keylime was accepted as a CNCF sandbox project.
Okay, so first let's go through some of the key technologies that we use in Keylime. So the first is a TPM, the Trusted Platform Module. What's it? It's a piece of hardware that is capable of performing crypto operations, like generating keys, signing data, and storing key. It is available everywhere, on laptops, on smartphones, on servers, everywhere, basically. What is so special about the TPM? It contains a key pair called an endorsement key. This key pair is generated during manufacturing and is immutable, so you cannot take it out of the device or modify it. The manufacturer signs a certificate for that key pair, so we call it the EK certificate, and they publish the CA certificate that signed it in somewhere public, so you can verify the identity of that TPM using the certificate. So since it's immutable, you have a unique identity for that device, for that TPM. So the point is that we don't trust the software directly, but we trust on the hardware root of trust, which is the TPM. The EK certificate has some limitations. It cannot sign data directly, but you can generate another key pair, which is called the AK key, the attestation key. It's associated with the EK in a way, so many Ks, right? But it's associated in a way that you can verify that something signed with the attestation key came from the TPM you expected. So another key feature of the TPM is that it has some special registers called Platform Configuration Registers, PCRs, that are designed to store measurements. So, and the TPM can generate a quote, which is basically the values stored in the PCRs signed by the AK certificate. So if you have the public key, you can verify the signature, and then you can verify that those measurements were legitimate. So how does the TPM store the measurements? It's through this operation called the PCR extension. So the PCRs can only be modified using this operation. And this operation is basically you replace the value of the PCR with the previous value concatenated with the new measure, and then you hash everything and put together back into the PCR. So basically it creates some structure similar to a Merkle tree, when the final value depends on all the values that were added before when you were measuring. So it can be seen as a summary of the history of all measurements that were used to extend that PCR. So if you have the log with all the measurements that you extend to a PCR, like a log, you can replay, like creating the extension and adding each measurement, and you have this final value that you can compare with something that you expected. And if it's the same, then you are sure that, those same steps were performed, the same extensions. So that's how you use the TPM to verify the integrity of stuff. This final value is also called reference value, or sometimes golden value.
So another concept that is important to understand if you want to understand Keylime is measure boot. So what is measure boot? Sometimes TPM, actually TPMs are often associated with secure boots, as sometimes they were used by some companies to vendor lock the hardware by preventing it from booting another operating system than the one it was shipped with. However, TPMs have broader applications such as measure boot. So in measure boot, the kernel measures the BIOS EFI layer and extend those values into the TPM's PCR and the boot log. This process includes measuring boot images, OS arguments, firmware blobs, and more. It's important to note that measure boot is not the same as secure boots. Secure boot halts the boot if the process fails, but measure boot collects the measurements, makes them tamper-proof, and allows for a comparison of the PCR values with known good values. And you can also follow the boot log to reconstruct and validate those PCR values. The key difference here between secure boot and measure boot is that the secure boot can stop the boot process on failure, whereas the measure boot leaves you the freedom to take the appropriate action if there's some policy failure. So it's purely informational. Another concept is IMA, we haven't introduced yet. So IMA is the acronym for the Linux Integrity Measurement Architecture subsystem. It is responsible for calculating the hashes of files and programs before they are loaded, and it supports reporting on the hashes and validating if they adhere to a predefined list of values. So IMA was introduced in the Linux kernel in the version 2.6.30. It has three subsystems, which are called measure, appraise, and audit. The measurement component collects the hashes of files. That includes executable and libraries by hooking it to the kernel. The appraisal component compares a collected hash to a stored hash, and it can deny access if there's a mismatch between hashes. And finally, the audit component includes file hashes into the system audit logs, which can be used to augment the existing security system analytics and forensics. So when a TPM is present on the machine, the IMA measurement can be extended into the TPM PCR.
So what is file integrity? Is the file exactly what you expect it to be? So you can check the integrity of a file by comparing the hash, a cryptographic hash that you calculate over it with an expected value, or verifying the signature if it's signed. So this table is about what you can get by using only hashes or using signatures in IMA. You can see that each approach has different usages and assurances that it can provide. So for example, it is not possible to verify the origin of a file if you are using hashes alone. You need to have signatures so that you can check the origin of a file. So in the other column about signatures not being rollback proof is because once the file is signed, the signature is valid and trusted, while the key that signed it is still trusted. So for example, if a company releases a new version of a package that is signed, it doesn't invalidate the older version of the package. So if the previous version has some vulnerability, let's say, it's still trusted, right? Because the signature is still valid. So you can see that in this case, the rollback can be dangerous. In the hashing, on the other hand, you can, it is rollback proof because you will have to have the new values of the hashes, like the hashes of the new package will not match the old ones, so you will get the mismatch. About easy to set up, this is about the infrastructure that you need to sign artifacts and verify, so you have to deploy the certificates, have keys, etc. Whereas with hashes, you simply calculate the hashes and store as the expected value, and that's it, nothing else is needed. On the last column, about being update friendly, it's exactly kind of mirroring the problem with the signature, because if the files, if you are using signatures to verify the validity of the origin of stuff and the integrity of files, then it is easy to update because it will be signed by the same key you already trust, so you don't have to change anything. You, on an update case, you will simply sign the new package with the same key and it will be trusted. Whereas with the hashes, you would have to update the reference values with all the hashes of all files that were modified. So IMA signatures can be shipped by the OS vendors. It is included in Fedora since the version 36 and also in RHEL 9. Yeah, one detail about Keylime is that it can use both approaches. It can use an allow list, which is basically a list of files and their respective hashes, and also use a keyring of public keys to verify signatures. So you can mix and match these both approaches. Okay, so what is remote attestation? It is basically a mechanism to verify the integrity of remote systems. So you check that the remote system is in a state you expected. So if you have the log of all PCR extensions that were performed during the boot process, and you have all the measurements, the log of all measurements made to the files and extend into the PCR, and you have the PCR values, like signed by a TPM, so you have the TPM code. You can use the TPM public keys to verify that the code is valid, and then replay the logs and compare the final value with the signed value that you verify that is legitimate. And that's how you verify the integrity of a remote system. So you have reference values, you get the information you got from the monitored system, and calculate the operation, the cryptographic operation, the PCRs that you expected, and compare. If they match, then it is in the state you expected.
So now let's see a bit more about Keylime's architecture. So Keylime components can be divided into two main parts. The first part is the monitored host, and the second one is verifying components. The monitor host is the machine that provides its integrity to the rest of the Keylime system by generating and sending attestations. So this host machine must have access to some type of TPM, ideally a hardware TPM, but Keylime can also work with virtual or software TPM, such as in a virtual machine, for example. The monitor host runs a Keylime agent, and you could have thousands of those hosts, actually, but in this diagram, we chose to just illustrate one for simplicity. But it works with a very large number of nodes. The other components are responsible for verifying the states of the agent nodes and taking actions based on the verification results. So you have a component that's called the registrar that acts as a key store, and it tracks public keys that are also associated with the agent's unique identifiers, but it does not perform the verification itself. Instead, the verification is performed by the verifier. So the verifier checks the remote attestation that is sent by the agents and ensures that the attestation is signed by the appropriate TPM key, and that the measure boot states or the runtime states in the TPM quotes. So a quote is a signed report of the current PCR values. matches the reference values that are specified by the measure boot policy and the IMA allo lists. The communication between the agent and the verifier or the registrar can occur over an untrusted network. And the verifier and the registrar, in this case, could be located in a different public cloud from the agent or on premises, and which creates a true hybrid cloud scenario. The network they communicate with can be untrusted because integrity checks are performed at each step of the process, and some pieces of information are encrypted with a public key that corresponds to one of the agent's TPM keys.
So let me explain the steps needed that Keylime perform, the workflow. So the first step is the registration. So the Keylime agent that is running in the monitored system will contact the registrar when it startups and sends the information about the identity of the TPM. So basically the certificate, the public key, and the registrar will associate both like the public key and the EK certificate together. Then the verifier will get the agent from the database that registrar stored and will ask for an initial code. So the agent will send an initial code or called identity code, which is the code of the state, current state of the agent. The verifier will verify that that code is valid by using the public key that was provided in the first step. And upon a good verification, like when the state is attested, then the verifier can optionally release some payload and send to the agent. So after that, the verifier will periodically request a quote to the agent and verify the attestation. By default, is 2 seconds. And if one attestation fails, like in case of failure, then you can configure some action to be performed. For example, you could configure a webhook to notify or some script to run, and this notification can be sent also to the agent. So, of course, it doesn't target the affected agent because it's compromised. You don't care about it. But the other nodes may need to know something about the affected agent, affected system. So, and everything is configurable here. You can choose if you want to send some payload or not, if you want to check the measure boot, which is the state, the measurements made during the boot or during runtime or both. You can choose the allow list for the policies, like change the policy and expect different values. And you can, of course, configure the action that will happen in case of attestation failure.
So we can also secure Kubernetes clusters with Keylime. So let's see exactly how it can work. So deploying Keylime currently can be a bit of a tedious task. But however, recent efforts in the Keylime community aim to simplify this process by enabling Keylime deployments on Kubernetes or OpenShift. The Keylime attestation operator is a project that facilitates this easier deployment and also management of Keylime through Helm charts or a deployment based on operator SDK. This operator monitors nodes within the cluster where it is deployed, and it can also register nodes outside of the cluster in external and potentially less secure locations, such as, for example, edge nodes. So deploying Keylime in Kubernetes or OpenShift can offer some significant advantages for responding to attestation failures. For instance, if a worker node that is monitored by Keylime is identified as compromised, the revocation events can trigger Kubernetes commands such as drain and cordon, and it can allow to quarantine the affected node from the rest of the cluster. This effort is still a work in progress, and contributions are encouraged. The long-term vision for the operator includes different things such as making Keylime available in the operator hub, adapting it to specific OpenShift configurations, generating policies based on configurations, and also ensuring the state of the cluster is accessible to external services.
So I will talk a bit about another feature implemented in Keylime. So Keylime can attest the current state of the nodes, the monitor nodes, but it is in an online fashion. So how do you verify the state of like a previous state of a node? Or what if that node doesn't exist anymore, like if it's offline? So the way they figure out was implemented this durable attestation, which basically stores all measurements provided by the agent into some database. Here the example is the record, the transparency log. It is important to be like publicly trusted, so it shouldn't be under the control of the person that controls the attestation infrastructure. So you push there the measurements you received from the agent, and then later in time you can recover that state at any point in time and verify that it is in a attested state. And you can even check that against different policies from the time the measurement was collected. For example, if you had some package with some vulnerability and you wanted to check in the past if some node had that package at that point in time, then this feature is what you need to verify that that state includes or not that affected package. So this provides make it auditable, the past states of the remote machines. So that's a superpower. You can not only have the attestation online at the moment you are measuring it, but also later in time, even when the node doesn't exist anymore, because you stored all the measurements.
So now let's take a look at Keylime's future, and in particular, the attestation of containers. So that's one exciting possibility, but unfortunately, currently, different obstacles prevent this feature from actually being implemented in Keylime. So a key challenge with attestation for containers is that files within containers can share paths with files in other containers and on the hosts, which is lacking segregation by container ownership in IMA. But also each file's measurement is sent to the TPM, which can sometimes make it difficult to differentiate between them. However, some ongoing efforts may enable container attestation in the future, and this effort includes different things. So one of them is implementing IMA-aware namespaces in the kernel, but also supporting VTPMs directly in the kernel, so each container could be extended to its own virtual TPM, but also container IMA using eBPF. So this latter approach aims to extend IMA with namespace support without altering the host operating system, and it's doing this through a Linux security module hook, or LSM hook. These developments could pave the way for effective container attestation and enhance security in containerized environment as well. So if you want to find out more about Keylime, you can get in touch with us. You can visit the main Keylime webpage at keylime.dev, but also under the cncf.io website in Sandbox projects, you can find the different repositories under the Keylime organization on GitHub. And finally, you can chat with us on Slack under the CNCF IO Snack and the channel Keylime. Thank you.
Thank you.
Are there any questions? Let's check the pool.
Oh, clear. It was perfect. That's the information.
Okay, we have a question here. Can the remote attestation be integrated into authentication, authorization on an application level? for example, for various APIs so that only verified node can use it?
That's an interesting use case. But like currently, there is no such thing like associating the attestation with the authorization. So you can attest the node that it's in the state you needed. So you can be sure that everything that is running there is what you expect to be. That probably provides already the guarantees you need, but I'm not sure. Like, if you want to, for example, segregate or make only some APIs available depending on the attested state, then you would have to implement that separately. But yeah, so it's kind of out of scope for Keylime. It can provide the attestation, and then you can go from there and decide what is your policy.
Any other question? I have one. So where do you see cloud providers are going? Do you see them adopting or...
Sorry, once again?
Cloud providers, so like major AWS, Google.
Okay, so the major cloud providers are providing some TPM-enabled instances. So for example, on AWS, you can get Nitro-enabled instances that can use the TPM. So, and they are basically implement their own attestation mechanism. Each cloud provider is kind of trying to provide their separate attestation mechanism. So this is kind of the state. The current state is that there are many different fronts or different projects trying to provide the attestation, but basically there are some big challenges that affect everybody. One, for example, is the lack of the measurements. So the vendors don't distribute the reference values for the artifacts. So even Red Hat doesn't provide the reference values for the artifacts. So it's difficult for you to create a policy beforehand. And so, for example, you want to restrict only, I don't know, artifacts from some provider to run on your system. So there's no way unless you create like manually, try to create a list of things that are provided by that provider. So it's difficult. So how I see is that many people are trying to provide attestation in many different ways, but it's all separate efforts. So.
Great, thank you very much. And I don't see any raised hands, so thank you very much for the presentation. It was great.
Thank you.